Hi class, how are you? Mr. Gray here, doing another video on scientific notation. Okay, so this is our first introductory day of it. So I'm going to go through the introductory steps. I'm going to give you some different problems to do today, and like I said, we're going to hit more about it next on Thursday and Friday's classes. We'll get some harder problems, and then finally, Monday, I think the Monday Tuesday classes will be pretty much close to done. Just a reminder, make sure you understand the 28th is progress reports come out. I don't know exactly what date was the deadline, but I will get that information to you in class today. So make sure you're aware of that if you have anything to turn in. All right, so what is scientific notation and why do we use it? Okay, scientific notation is basically a way to make large and smaller numbers workable. Okay, so the idea is that if you have a big amount of money, it's like $1 billion or whatever, like the Sir Knight and Mr. King, Sir Knight Maddox, and then we had King Zhang there talking in their situation. So basically, we need to figure out, okay, how do we make those workable numbers seeable on the calculator, but also seeable so you guys can also figure it out as well. So, like, how much is $1 billion? I don't know how many zeros are in that. Okay, but if I make it in standardized notation, I can kind of figure that out. All right. So let's look at the number that we just talked about from our Mr from King Zhang and his reward. So we have 1.88446744073771 e to the 19th. Okay, so like what the heck does that mean? Okay, so this is actually technically standard scientific notation. Okay, not standard form because that's the opposite. Scientific notation. So basically, what has happened here is we've actually made the actual what the value is, and this e to the 19th represents how many zeros are after the decimal place. Okay, so let me show you what I mean. So if you think about it, e to the 19th, what is that actually? The e means exponent. Okay, so when we do scientific notation, we're going to write the exponent or how many zeros there are after the decimal in a base power of 10. Okay, so this is going to be a 10 here. If this thing makes it. Oh, come on, come on, come on. Yeah, there you go. And then this is going to be 19. Okay, so that's how it actually really represents 10 to the power of 19. So basically 10 times 10 times 10 times 10 is 19 times. Whatever that equals, then we're going to multiply it by that number here. But there's an easier way to do that so you don't have to do all that multiplication. Okay, so all you have to think about is basically from the decimal point here, I got to go 19 spaces to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then I got to add zeros from here. So I go 12 spaces. Hopefully I can get there. But the thing is kind of not controlling me here. 0, that's 13, that's 14, that's 15, that's 16, that's 17, that's 18, that's 19. Okay, so I'm gonna count it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. No, oh, 19. Oh, shoot, I gave you 20. Shoot. All right. Let me just hide this here. Take this away. Take this one zero away. Okay. So again, that is 19 spaces. Okay. That's a lot of money right there. So again, King Zhang is really a generous person if you think about it in terms of like the chessboard. Okay. So Maddox, if you took the $1 million, was actually not a smart man because again, think about it. You start cutting zeros here. That's a lot of money. Okay. So again, it's just an easy way to write it. Now, again, this is one thing that you need to see in regards to these scientific notations. Okay, so if it's a positive number, we're obviously going to go right to make this value bigger. But how do we represent it if we want to make it smaller? So say we have a little beaker of solution that we want to put in like a mixture or something like that, and it's like 0.0000674. That's how much we need. And so how do we represent that? So let me show you that one. So let's take this same number and maybe we won't do as much, but there you go, 0, 0, 1, 8, 4, 4. Okay, so it's actually pretty easy. And again, we'll show you a couple more examples. All right, so the rule is it always has the in scientific notation, the expression that we make is basically have to be between the first two numbers in the first original two numbers in the series. So the 0 and 0 is not the is the numbers, but that's kind of like the ghost zeros. But these two numbers right here is between the 1 and the 8. So if you think about it, how many spaces did I go to the left to get to the back of the 0 here on the left? So I go 1, 2, 3 spaces. So how I would rewrite that would be 1.844 times, come on, baby, come on, 10, times 10 to the negative 3. So that's how you would write a situation like that. So again, if you want to make it smaller, you go from that 1.8 portion, and you got to make it 3 spaces to the left. So I make it negative 3 if I go left. Okay, does that kind of make sense? All right, so let's try that again so people can get an understanding. People are like, oh, I kind of get it, but I'd like to see it one more time. There you go. All right, so let's talk about this again. We have 6710000. We have 4 zeros here. Okay, so we have to take that and put that into scientific notation form. So the idea we said before was, okay, so if this is the whole number here, this is where the original dot is. Here's the dot we want to have. Okay, so we want to be between the first two numbers in the series here. So let's count over. 1, 2, 3, 4, 5, 6. So basically, I rewrite this as 6.71 times 10 to the power of 6. Oh, that's a nice 6. Okay, so that's how it would work in that situation. Okay, so again, now the other way, same idea. We got to be between the first two numbers, so so that new spot has got to be here. So let's count over 1, 2, 3. Okay, so it's basically 3.51 times 10 to the power of negative 3. And that's how it would work every time. Okay, so again, if you're starting at the edge here, we got to get all the way to this point. So count how many zeros there are. We're going to start. If we start at the edge here, how many points does it get to be between the first two like numbers here? Okay, I don't call zeros numbers because like they're just values. All right, but like I said, these first two numbers, boom, it's right there. Okay, so you just got to count those spaces, and that's going to be your exponent. Okay, so I think we kind of get the idea of how this works. I could show you the other way, but I don't think we really need that. I mean, at this point, but I mean, I think you can count the zeros from this point, do it the opposite way. So converting back, okay, which is standard form, and I think we can figure that out. All right, so I'm going to trust your judgment on that. So let's move on and try some harder problems here. Okay. All right. Oh, I forgot to mention this. All right. Now this is also important as well. Okay. Now looking at this, we have 4.5. We have 45.68 times 10 to the power of 5. Okay. Now, if you look at normally, like, that's fine. What's wrong with that? This is standardized notation. I'm good. This is the answer. Well, technically not. It's not the answer. Okay. Now, standardized scientific notation. Okay, in scientific notation, you have to have the decimal point always has to be between the first two numbers in the series. Okay. So instead of being between the 5 and the 6, it actually should be between the 4 and the 5. Okay, at all times. Okay, so every time you write it, it always has to be between the 4 and the 5. So therefore, to make that happen, I always have to have 1 added to the exponent if this is the case. Okay, all right. So I got to add 1 to the exponent. So technically, the real answer should be 4. Okay, 0.5 times 10 to the 6th. Okay, so it should be just like that. 4.5 10 to the 6th. Okay, instead of the other way. All right. So this would also hold true in this situation as well. So we have 24.7 times 10 to the negative 6. Okay, yeah, all right. It looks good, but again, we talked about it has to be always between the first two numbers in the series. So it's always going to be right here. instead of right there. So it's still, and again, we have to add 1 to the add 1 to the exponent. So our new equation should be new scientific notation should be 2.47 times 10 to the negative 5. Okay. All right. So I think we kind of see that, but I'm not sure. I mean, you're going to see it when you start doing the actual, I'm going to do some problems right in a little bit. So you're actually going to see how that actually works and changes the answer to the equation and stuff. But that is important to understand that always has the decimal place point always has to be between the first two numbers in the series, cannot be anywhere else. Okay, so you have to make sure you add 1 to the exponent or whatever, how many spaces it over to make the exponent just like that to be standardized notation. Okay, so that's a little tricky spot, and that will be on the quiz, and you will have to do that. If you don't, you're not going to get full credit. Okay, so let me see. So guys, like, okay, I kind of see what you're saying, but I really don't. All right, so let me show you what I mean. Okay, so if you think about it, right? We have, if we take this one, we got if we have this, we have 24.7 times 10 to the power of 6. So basically what that means is I'm going to add 4 zeros, this, and that's going to be what my answer is going to be. Let's take a little time here. Okay. And it's right here. All right. So again, moving the space 1, 2. Now from here, 1, 2, 3, 4, 5, 6. Okay. That's great. But technically, like I said, with real standardized notation, what the difference is, it actually should be right at from this point, not between the 24. So it should be from this point. So that's why it becomes 1, 2, 3, 4, 5. Okay, because again, it just depends on where the decimal point is. So hopefully you can see that and make that adjustment when you are doing the work when we have the class. Okay. So if you have any questions, please let me know. I know this is kind of I'm going to go in quick, but I want to get this done. All right, so let's try some problems here. So this is something that you're going to have to do in class today. Some problems. All right, so we have a situation here of 4.9 times 10 to the power of 3, 2.8 times 10 to the power of 2. Okay, now I'm going to tell you that you're going to use multiplication rule in this situation. Okay, and you're like, why the hell would I do that? Okay, well, you don't technically have to do that. If you wanted to, you can take 4.9 and multiply that by 10 to the power of negative 3 in your calculator, and that will give you an answer. And then you take 2.8 times 10 to the power of 2 and multiply that, and that will give you your answer. And then multiply both numbers. But after that, you have to turn that whole equation back into scientific notation. Okay, you could do that if you wanted to, and that would take care of the whole problem. So you don't really have to do this technique, but it's good to learn and make sure you practice the law of exponents. So again, make sure you if you do it the other way, make sure you have the right answer. Okay, so multiplication rule. What do I mean? So basically, I mean that I can take 4.9 and I can multiply that by 2.8, and I can multiply 10 to the power of 3 times 10 to the power of 2, and multiplying both those things, I can get that standardized in scientific notation, and that would still be the correct answer. So let's think about it. 4.9 times 2.8 is 13. Oh, I'm going to make it better 3. 13.47. Okay. Now, from here, now the multiplication rule says if you have the same basis of 10 and 10, which is the same basis, I add the exponents. So I have negative 3. And I add, oh, wow, looks like a boom. Pretty cool boom. Okay. Plus 2, and that gives me a value of negative 1. Okay, so therefore, I just have a value of 10 to the negative 1. Okay, and that would be my answer to the question. That's all I'd have to do. Multiply the 4.9 times 2.8 and give me the number, and then add the exponents, and I'm done. It's pretty easy, right? However, what are we missing? Okay, so remember, like I said, that the decimal has to be in between the 1 and the 3, not the 3 and the 4. So I got to move this over one space to the right. So I add 1 to that. Okay, like we said before. So again, our new answer is going to be 13.43, 1.347 times, I'm 10, technically to the power of 0. Okay, which is technically just 1. All right. So again, like, see how this is starting to work with the law of exponents and all this stuff trying to mix together. This is how math works all the time. Okay, so that would be the answer to that question. All right. Again, that would be the real answer. So on the test, if you give me this, you're not gonna get credit. This is gonna have to be your answer. Okay, or you could just say 1.37 and it'll be the same answer as well. Okay, so let's look at the next one. All right, so we have same idea. Using the multiplication rule, we're going to multiply 7 times 7, which is 49. Okay, it's going to give us the answer. And then we have -3, and the other multiplication rule tells us that that we're going to multiply, when we multiply with the same basis, the exponents are going to be added. So that would be -3 plus 0, which equals -3. Okay, so that would be 49 times 10 to the -3. Okay, 10 to the -3. All right, so how does that work? Okay, now think about this. Okay, we said that before, that to do this correctly, we have to move the decimal place into the middle between the 4 and the 9. So again, we got to add 1 to this exponent here to make this work right. Okay, so then our new answer should be 4.9 times 10 to the -2. Okay, so again, make sure you see what I'm just talking about again with those values, because that can really mess people up if you're not listening and not figuring that out. Okay, so again, we're gonna practice this for a couple of days. So don't worry if you don't get it right now. We will practice and we will get better at it, and you will be a master by the time we have a quiz or a project. I think we're gonna do a project on this, so be prepared. All right, see you guys. Have a good day. Have a good day. Turn this thing off.